Hi Chemistry 12-2 and welcome back. This is our third video for week 9 and we're going to take a look at two new organic reactions and we're going to take a look at two new families, no actually three new families, and talk about how to recognize them, how to name them, how to draw them. So here is a quick summary. We've talked about substitution and addition reactions to date. Substitution reactions is just like the name says, substituting in one for the other. So we're going to take a saturated, and this is how you recognize it. You start with a saturated, so an alkane, and you're going to take off an H and substitute in a halogen or an OH. When we substitute a halogen in, we make a halocarbon. When we substitute an OH in, we make an alcohol. And here's a couple examples of those. With addition, it's different because we start with multiple bonds. And what we're going to do, so we're starting with an unsaturated solution, and those double bonds can be broken so that we can add branches. And so we are going to add two things. Once we break our double bond, it opens up some valence electrons so we can add two new things to our compound. This video we're going to take a look at elimination and complete combustion. And then in our last video we'll take a look at esterification. So let's go right to elimination. So with elimination, we're going to eliminate something. Yep, you guessed it. But just like before, you need to know how to recognize it. So this guy's going to start with something different than all of the others. With substitution, it starts with alkanes. With addition, it starts with alkenes or alkynes. You need a double bond. With elimination, you're going to start with a halocarbon and with the OH ion, the hydroxide ion. So you need both of those things present in order for it to be an elimination. And what we're going to do is by eliminating one of our branches, we're going to create a double bond. So during an elimination reaction, halocarbon reacts with a hydrochloric ion to produce an alkene, so we're going to make a double bond by removing a hydrogen. And this also will result in water because that hydroxide will join with the hydrogen that we eliminate and therefore create water. So let's take a look at a couple examples. So here we have, we would call it 1-chloroethane, right? This is its common name, but 1-chloroethane. So it's a halocarbon, it's got chlorine. We're going to add, because we want this OH ion, and it doesn't exist on its own. So it's going to bring potassium with it, but as soon as it dissolves in water, we're going to have OH ions and K positive ions. And so what happens, and we've got our two things, so we've got our halocarbon, and we've got our OH ion. So what happens here is the halogen leaves. So we're going to eliminate the halogen, and when we eliminate the halogen, we free up an oxygen here, a valence electron here, and if this loses a H, we can have two valence electrons. And so that's what happens here. We make this double bond, and the Cl is now on its own. It's a negative ion, so K comes over and says, hey, I'll hang out with you. And the OH now has water. It's a little tough to see with these, so let me jump down here and I'll show you an example. So we can move around these parts. Here we have 2-bromopentane. So we have a halocarbon. There's our bromine. We have hydroxide ion. It's coming to the party with sodium, but as soon as it gets into the water, they break up into their ions. So what's going to happen here? Well, what happens is, this is where elimination, we eliminate the Br, but at the same time, we eliminate an H. Now, they're not going to hang out together, but we do eliminate both of those things. And by eliminating both of those things, what happens is we have, let's see if this will let me do it. We have a free electron there and a free electron here. So we've got two of those valence electrons. And what this guy says, I'll bring him over here, he says, hey, let's not go looking for anybody else. Let's make a double bond. So eliminations create double bonds for us. So this was a alkane, and now it's an alkene. So that's what happens to those. So when we eliminate them, though, what happens here is the hydrogen says, hey, why don't we hang out, okay? And the sodium says, hey, why don't we hang out? So we actually end up making an alkene. We make a water molecule, And we have this ion that's floating around, and if there's a positive ion in the beaker, they'll join together. So these are the three things that we make. We've got to be careful because that was one way the elimination could happen, right? And those were the three things that we make. But there's another way that this elimination can happen, and that's if not this hydrogen, but this hydrogen leaves. So let's bring this hydrogen back. Boom. And we'll put them right back here. We'll just take our little extra electron out. And the bromine does leave, so the halogen always leaves. But what if this hydrogen left to make water? Okay, what's the difference? The difference is that now when these two carbons say, hey, let's make a double bond, we've got these free electrons, the double bond's not between the 1 and the 2, the double bond's between the 2 and the 3. So those are isomers, and we've talked about that before. Sometimes we'll actually make a combination of two different substances. Now, because it's an organic reaction, we've got to name these things, right? So NABR, we're jumping back to grade 11. That's going to be sodium. I'll just bring this over and clone it so I've got the same font. That's going to be sodium bromide. And up here, you can use the common name if you want. All right, and we're going to call that water. But again, we want to name these things because it's an organic reaction, so we want to name them. Tell your friends not to forget to name them. Your assignment has 9 of these guys, so you got to figure out what kind of a reaction it is, then you're going to predict the products. So here, these are going to be pentenes, but where the double bond, I didn't write my hydrogens, but where's the double bond? So these are both pentenes because they have a double bond, but indicate, so pentene, this could be just one, so you could leave that one out if you wanted to. But this guy's going to be 2, so they've got different names, different isomers, and we have to look. So there'll always be 2 options, unless you know, your BR is on the front. There's only one place for it to go if the BR was on my first or last carbon. But the fact that the BR was one of my middle carbons, there were 2 possibilities. So we can eliminate, we always eliminate the BR, but we can eliminate a neighboring hydrogen. In this case, we eliminated the hydrogen to its right. In the first case, I eliminated the hydrogen to its left. Okay, so that is an elimination reaction. You need 2 things. You need your hydroxide ion, and you need a halocarbon. So this was a halocarbon, if you recall. All right, so let's take a look at another couple examples, and then we'll move on. So here we have prop, right? So propane, 1-chloropropane. The chlorine is on the first carbon. So here's another hint, elimination. It's got an OH. So we're going to eliminate the Cl and a neighboring H. When we do that, it frees up 2 electrons. So there's a double bond here now between this. So it's just propene. Because the C was on the last, Cl was on the last carbon, there wasn't an option of which neighboring H to take. There's only one neighboring H. So there's only one compound that it creates, KCl and H2O. So H2O will always be a product. The ion itself, the halogen itself, if there's another positive ion in there, it'll probably join up, and then you've got your double bond. Here you can see that the Cl is here in the center, and it's 3, and we're adding the OH. So it's not an addition, and that's sometimes easy to mix up. We're eliminating the Cl, and we're eliminating an H, and the OH is picking up that H that we eliminate. Okay, let's try one more. You guys try it. So pause right now, take a piece of paper and a pencil, and predict what are the products going to be here. Pause, try it on your own. Come back when you're done. So we know it's an elimination because, thanks for coming back. If you really just waited for a minute, go, really, pause, go, figure this out, come back. Welcome back. So what we have here is a prop and a B. So this would be 2-bromopropane. We always name our compounds. We've got our hydroxyl. He didn't bring a party favor with him, right? So he's just the OH. Sometimes you see it like this. Sometimes you'll see him with a positive cation with him. So we have our halocarbon. We have our hydroxide ion. and we're going to eliminate. We always eliminate the Br, right? And we can eliminate a neighboring hydrogen. We can eliminate this guy or this guy, but be careful. In this case, when we eliminate this guy, here's the double bond. In this case, if we eliminate this guy, this is the double bond. With prop, though, you can count either way. So there's only one ion, one ice. There is not an isomer. There's just one possible compound you can get here with this, okay? And there you go. Right, so you're getting one propene, your bromine ion, and your water, and that's the structural formula for water. Okay, so elimination, practice some of those. The other type I wanted to talk about, we've talked about before, so I'm going to spend about 35 seconds on it. Complete combustion. We have talked about the combustion of hydrocarbons for at least 2 years, since grade 11 chemistry. And when it comes to combustion, it is the mixture or the reaction of oxygen. And when it reacts with a hydrocarbon, it reacts with hydrogen and it reacts with carbon. So you always get the exact same products. You can vary in the amount of molecules, but you get the exact same products when you have a complete combustion of a hydrocarbon. Incomplete combustion can happen if you have a decrease in your flow of oxygen. So when you have excess oxygen, more than enough oxygen, you have complete combustion. If the levels of oxygen are low, you sometimes will have incomplete combustion, and that is when carbon monoxide is formed. So here are the two equations. We're going to take methane, which is a hydrocarbon. If we bond it with oxygen, the oxygen is going to react with the carbon to make CO2 its common oxide, and oxygen is going to react with the hydrogen and make H2O its common oxide. We also know from chapter 10 that this is definitely exothermic, so there's lots of energy being created. A combustion reaction is always exothermic. Here's an example. If you're lighting your Bunsen burner, if you open your air hole enough, you are going to have a nice blue hot flame. This is complete combustion. If for some reason there's not enough oxygen via the air getting into the flame, then you have a very different flame. So this is complete combustion, this is incomplete combustion. We're not going to worry about the incomplete combustion. It gets a little more complicated. What we need to know is any type of hydrocarbon, an alkene, an alkyne, an alkane, it doesn't matter. Any type of hydrocarbon, if you add oxygen, you're always going to make these products. But it's nice to know the structural formula, right? We're not going to write the molecular formula, we're going to write the structural formula. So carbon forms 2 covalent bonds with oxygen over here and 2 covalent bonds with oxygen over here. The double bonds work as linears, so this is a linear shaped molecule. Over here we have water, 2 H's and an O. Because of the unshared pairs of electrons, these bonds get pushed down a little bit. So this is the V shape when it comes to Vesper. So important to know the structures of those two things. These are probably the only organic reactions that we worry about balancing. And so we've balanced these before, and you can continue to balance them. Okay? So complete combustion. This will take 2 more places in our table. So when you look, and I want them all kind of side by side so you can see how you recognize them. So here, easy to recognize, you need that halocarbon, and you need a compound with OH, right? So you need that hydroxide ion. What's it going to make? It's going to make an alkene, so it's going to make a double bond. When you eliminate 2 of the one H and one halide, you're going to create a double bond. You're going to create water because that H that you eliminated joins up with the OH, and you're going to have an halide ion, and it might have something to join up with. Okay, so there's an example we looked at. With complete combustion, we're looking at hydrocarbons specifically, so you need a hydrocarbon and an oxygen, and you're always going to make carbon dioxide and water. Right? The number of molecules of each will change, but that's what you're going to make. And there is methane. I take note, all of these guys start with different things. Keep this chart handy if you are starting your work with the 9 questions on the assignment about predicting products with your organic reactions. All of these reactions start with different things, and that helps with identifying them. We'll talk about esterification in our 4th video. So this leaves us a little bit of time to talk about 3 new families. And the first family I want to talk about if I can find it, is going to be ether. And we've talked a little bit, oh, I was going to throw this in. I will throw this in. This is not one of our 5, but sometimes you might hear about cracking reactions. Cracking is just what it sounds like. We crack a large hydrocarbon into smaller hydrocarbons. It's what's happening at Irving right now. So when we are refining oils, many crude oils are long chains of hydrocarbon, and we want to break them into workable products like propane or butane or things like that. So if you take a very long hydrocarbon and you break it into smaller hydrocarbons, it's called cracking. Okay? So if you hear about cracking reactions, that's what's happening, breaking them into smaller groups. Okay, ether. So ethers I find really interesting because of their previous use. So when you talk about surgery and you talk about getting anesthesia, the first anesthesia that was used was an ether in the Civil War. And what they wanted to do is they wanted to, make your patient unconscious, because before that, if you had to have surgery, you were awake for your surgery, and it was extremely painful. When ether came along, one member of the ether family, they were able to use it in order to cause the patient to lose consciousness and also to have the patient's muscles relax. So the surgery was easier and a heck of a lot more comfortable for the patient when it happened. So it's just kind of a neat little historical point when it comes to ethers. And ethers are pretty easy to recognize. With ethers, the general formula, and remember, we're filling out a little form with all of our general formulas. The general formulas are OR. This is your functional group, that oxygen in the middle. So it has a carbon chain and a carbon chain. Those carbon chains can be identical. They can be completely different, okay? But there's a chain of carbon here and a chain of carbon here. Remember, oxygen only has 2 valence electrons, so it only gets 2 covalent bonds. So there's nothing above or below it. So you have your carbon chain, rest of the molecule, and this is the tip of the iceberg, your functional group. This is what's going to create some chemical properties that we'll talk about in a minute. So they're pretty easy to recognize because they have that oxygen smack dab in the middle, and they're named for those 2 R groups. So essentially, we're going to find the name for this guy, find the name for this guy, put them in alphabetical order, and then finish our name with ether. So it's a compound in which oxygen is bonded to 2 carbon groups. The alkyl groups attached to either linkage, to the ether linkage, are named in alphabetical order and are followed by the word ether. Symmetric ethers, which means the R groups are identical, are named using the prefix di, even though sometimes the di is dropped. So I'll show you an example. Here's some examples of some ethers. So here's the general formula. There's 2 unshared pairs of electrons, so they won't create bonds, but they do affect the shape of the molecule. Here we have our O in the middle, so we know it's an ether. We have a methyl group, right? So our R here has 1 carbon, so it's meth, and we use YL. Here, there's 2 carbons, so we treat them as branches. So these are branches on our O. So we have a methyl and an ethyl. The ethyl is named first, and then the methyl. We don't need any numbers because they're both attached to the oxygen. So ethyl, methyl, ether. Okay? Here, our O is in the middle, functional group. We have this benzene, but it's acting like a branch, so it's going to be phenyl. And we have methyl here, so we have methyl, phenyl, ether. Methyl first, alphabetical order. Down here, this is one of those symmetrical ethers, and it's a symmetrical ether because it has an okay, I have a hard time with this. It's an ether. It has an ethyl and an ethyl. So ethyl and ethyl. You can call it diethyl ether, or sometimes if there's just one branch and they say ethyl, they say ethyl ether, then it's understood that both of the R groups are ethyl. Here's another symmetrical ether. You have a benzene, but it's a branch, so phenyl, and you have phenol. And so you would have diphenyl ether or just phenyl ether. Okay? A couple properties that are interesting when it comes to ethers. You can see because of the oxygen and the high electronegativity, the intermolecular bonds are hydrogen, so they're strong intermolecular bonds. They're not as strong as your halogens, but they're pretty strong, so you can create some very strong bonds. Ethers have high boiling points. They're usually higher than your hydrocarbons or your halocarbons, but they're going to be lower than your alcohols. Alcohols still have the higher boiling points. Why? Because they create more hydrogen bonding. And the more hydrogen bonding you have, the tougher it is to pull apart those molecules. So alcohols, highest boiling points, then ethers, then your halocarbons and your hydrocarbons, because they aren't really creating a lot of these hydrogen bondings. Solubility in water, we found that alcohols, the small ones, thanks to their OH, were soluble in water, so 4 or less are soluble. If you have a parent chain of 5 or more, it is less non-soluble. Same thing with ethers, okay? They're more soluble in water than hydrocarbons and halocarbons, but they're less soluble in water than alcohols. So they do have the solubility, but not as much. So alcohols seem to be the winner in all of those. How are we going to name them? Well, we've looked at a few. So if you want to pause now and name these first, and then I will quickly give you the names in a moment. But please pause, try them on your own, and then come back. So here's your line. So here we have 1, 2, and then here's our oxygen, 1, 2. So this is what we've seen, let me write, ether, T-H-Y, ethyl, ether. And sometimes you'll see there's a space there and sometimes there isn't, okay? Here we count 1, 2, 3, 4, 1, 2, 3, 4, 5. So this is pentyl, this is butyl, and we put it in alphabetical order. So butyl, pentyl, ether. Okay? Here, 1, 2, 3, 4, 5. Then your oxygen. 1, 2, 3. So pent and prop. So pentyl, propyl, ether. And pretty straightforward in the naming. All right? Excuse me. And this one here, your phenyl, you've got your oxygen, and then 1, 2, 3, 4. So butyl, phenyl, ether. All right? So those are some ethers for you, pretty straightforward when you're naming. Here's a little extra practice if you want to, and it's from your textbook. When you take a look, the last 2 families I want to talk about are in this video are aldehydes and ketones. And like I said earlier, they're kind of like cousins because they share the same functional group. And so they're very similar in chemical properties, but a few differences because the functional group sometimes is placed on the first carbon or last, depending on how you count, but it can also be placed on one of the centers. So the functional group is CO, C double bond O. So we might have recognized it as C O. And if we put our O up here, right? So this was our carbonyl group. And we had equal, and let's just rotate that around. And there was a double bond. Okay, so this is the functional group for both aldehydes and ketones. With ketones, it's somewhere in the middle. So they'd have an R on this side. Oops, it's a big R. They'd have an R. Well, maybe I'll make it smaller. So in your sheet, because I know you guys are filling out this sheet, you want to make sure you know the general formula. So the general formula for a ketone and an aldehyde are very, very similar. Is that about the right size here? Perfect. So they're going to have an R right there. And if you have another R, which is right where? There. So that's the general formula for a ketone, okay? Because the carbonyl group is somewhere on the middle on a middle carbon. The only difference for an aldehyde is you take this guy out and you clone him and you turn him into an H. And this indicates that the, right, so that is for an aldehyde because it's on the last carbon or the first carbon, whichever way you want to think about it. But if you swap that out and put an R here, now the carbonyl group is on a middle carbon. So that's the only difference between these two families. Okay? Aldehydes and ketones. A lot of people are like, how do you remember which one's on the end? This is how I remember. Aldehyde starts with an A. The alphabet starts with an A. So if it's on the starting carbon, it's going to be an aldehyde. If it's on a middle carbon, it's going to be ketone. So A for aldehyde, A for ABCs, starting at A. Okay, so let's look and see how we can name and draw these guys. And by golly, I might get this done in 30 minutes. Here we have the general formula. Actually, no, it's not a general formula. We have just one carbon, this poor little baby, just one carbon. It has a hydrogen, and it's double bonded to the O, and it's got its 4 bonds. This would be meth, right? Meth. And this is going to be, because there's only one carbon. And here we have, we've grown it. So now we've got 2 carbons. So this is your terminal carbon, and this is an R group beside it. So we count the terminal in our R group. So there would be 2 carbons. So this would be F. So ethane, methane. Here we have propane, right? But we have this double bond. So this is a ketone. This is a aldehyde, and this is an aldehyde. This is a very common, or you might have heard of this aldehyde. It's kind of been outlawed now. It is methanol, or also known as formaldehyde. Aldehydes, right? Formaldehyde. So this has been outlawed, but formaldehyde has been around for a long, long time. This is acetyl alcohol. Sorry, I should say this is acetaldehyde. It's hard to say, or ethanol. And this is propanol. And propanol, now remember, so let me just carefully say these things again. The IUPAC name for this, maybe you can figure it out. This is called methanal. This is called ethanal. This is called propanone. Propanone. So we're using the alkane, just like we did with alcohols. Remember, we used the same parent chain, but we dropped the E and put OL. Well, these are very, very similar. But for aldehydes, we drop the E and put AL. And for ketones, we drop the E and put ONE. So very similar to our alcohol family, except we're changing up the ending. So the endings for aldehydes are AL, and the endings for ketones are ONE, right from the end of their name. Okay? And propanone is actually acetone, and we have a lot of acetone in our fingernail polish remover. You can smell the acetone in it. So this is the chemical formula for acetone, propanone. Acetone is the common name for it. Okay? So here's the carbonyl group. This is a ketone because there's 2 R's, and this is an aldehyde because there's an H there. Okay, so let's get naming some of these things. So like I was saying, with aldehydes and ketones, we still go with the parent chain. It doesn't have to be an alkane. It might be an alkene. It might be an alkyne. But we start with the parent chain. We drop the E, and if it's an aldehyde, we put AL. And if it's a ketone, we put ONE. With a ketone, we need one more piece of information. Which carbon is that functional group on? So we'll see numbers with ketones. We won't with aldehydes unless there's branches, because aldehydes, the double bond to the O is always the last carbon, or the first carbon. Here, the double bond to the O might be on a middle carbon, so we have to indicate where that middle carbon is. Okay, but this is the rule for naming. And let's do a few names, and then we'll just take a look at a few properties, and we'll be good to go. So here we know, boom, as soon as we search for that functional group, we see the functional group, it's on a middle carbon, so it's a ketone. So this is going to be a ketone. And how we name it is we want, this takes priority, so the functional group always takes priority. So if we counted this way, it would be on the 4th carbon. If we count right to left, it's on the second carbon. So that's what we want to do. So this one is going to be, to start off, 2. Come on. 2. And it's a ketone, but it's on a chain of 6 carbons. So it's going to be hex. And it was ane, but we dropped the E and put O-N-E. So 2-hexanone. But there might be branches, and in this case there's a halogen branch here, but it's on the 6th carbon, okay? So 6 bromo 2-hexanone, okay? So a ketone, 6 bromo 2-hexanone. Here we have our functional group again. This time, look, it's on an H. This is on the last. So this is going to be a aldehyde, okay? That's not spelled right at all. It's an aldehyde, right up there. It's an aldehyde. And so what we're going to do is, again, look for your parent chain. We have 4. So it's butane, but it's got a different functional group. So we're going to take off that E and we put Al, not Ol like alcohols, Al, because it's an aldehyde. It's on the last carbon or the first carbon, perspective. You don't need a number, but it does have a branch. So we count from our functional group back. So 1, 2, 3. So 3-methyl butanol. Okay, 3-methyl butanol. I jinxed myself. I'm over 30 already. Here we have just a couple more. We have a double bond, and that's okay. So this parent chain here is butene, right? Here's the functional group. So I know it's an aldehyde or ketone. It's a aldehyde because there's the H. It's on the last carbon. So we drop the E and put Al. And we want to know where this double bond is as well. That's important, right? But this guy gets the priority. The functional group gets the priority. So we're going 1, 2. So it's 2-butanol. Oops, not there. It's 2-butanol. Right? And we have no branches. So we're done. Okay? So just be careful. People like to say, oh, is that where the double bond to the O is? No. We know it's at the end because of Al. That's where the double bond for the ene is. Here, phenyl, okay? It's a branch, and it's carboxylic acid now just by doing that. So it's actually, we could probably call it benzene, is how it starts out. And we can take that off and put the Al. So it's actually still a family of benzene, right? We're not, because a functional group can't be a family on its own. So benzene is our parent ring, and then we've got Al at the end to let us know that we have this functional group at the first carbon. And the only difference here is we could, I guess what I should do though to let you guys know that that is benzene and not just cyclohexane is actually put a circle in there so that you guys can see that, okay? Because we could name it a different way. I just automatically went to benzene, but if it had been cyclohexane, right, so if it had been cyclohexane, I just would have dropped that and put Al. So the ring, if it's a benzene ring or if it's a cyclohexane ring, that is the main part of the name, and then this is our functional group. Here we have cyclohexene. We drop it, put Al. We know these are all aldehydes because wherever we put that double bond to the O is going to be the first carbon. So we should probably include 1, 2 in front of this to show where the double bond is. Okay? Whew. One last thing, and I know I'm treading on thin water, but I will flash this slide up for you guys before you go. You can read it. But these are some of the characteristics, chemical characteristics you'll see when it comes to aldehydes and ketones. They're very, very similar. They have the same functional group. That's why they're similar. It's the placement of the function group that's different. With ketones, it's on a middle carbon. of the parent chain. With aldehydes, it's on the first. It looks like the last, but it's how we count. So it's on the first of the carbons. Okay, they form weak bonds. When the carbon chain is an aldehyde or a ketone, if it's bigger than 5, then its solubility is low. So with alcohols, remember, if you had 4 carbons or less, they had high solubility. If 5 carbons or more, low solubility. So it's the same thing here. You know, if they have more than 5 carbons, you're going to have low solubility, because the bigger the hydrocarbon, the more nonpolar it is. These functional groups are polar, so therefore the smaller ones kind of get through, and they will mix with water, but the big ones will not. They have high boiling points because they have very strong intermolecular bonds. They tend to be liquids or solids at room temperature, but there's one exception, methanol, formaldehyde. It is actually a gas at room temperature. Okay, so sorry, I did go over a little bit, but I hope you're okay with our 2 new organic reactions and our 3 new families, ethers, aldehydes, and ketones. Thanks so much. 39.